So, good morning, everybody. My name is David Bott. I'm the Head of Innovation at the Society of Chemical Industry, and I'd like to welcome you to this, the third in the series of workshops on rather cutely named Energising the UK battery supply chain. As I said, this is the third one in the series, and we ask in everyone, and you will be asked later this morning, what you would like to know more about, and recycling came up very strongly in the last two workshops, so this is about recycling. So what we've got is I will sort of give a quick introduction and then we'll move into three presentations by people who truly know what they're talking about. The first is Constance from APC. For those of you who don't know, APC is the Advanced Propulsion Centre. It's been going about 10 or so years, and its role is to fund the later stage projects in the implementation of the Automotive Leadership Council roadmap and various other things concerned with automotive. So basically, it's really important in making things happen in the real world, and Ian is the CEO there. So the fact that he's talking to this community is a sign of how importantly they view the whole recycling piece. The second speaker is Andy Abbott, who is from the University of Leicester, but you will see from his background that he's representing the Faraday Institution. He's part of a project called Reliv, which is about how you recycle batteries, and you will understand that more. And then lastly, we've got Mark Bedford from Johnson Matthey, who make a lot of money out of recycling expensive metals, talking about the problems that you get when you start recycling metals out of very complicated structures and so on. So it's a really, hopefully you'll learn a lot more about the needs for recycling, what's going on at the moment, and then some of the challenges over the next hour or so. Then, as is normal, we break into three smaller breakout groups, and you get a chance to ask questions of the people. You get a chance to say what you're doing, introduce yourself. These meetings are as much about building a community as they are about giving you the information you need to participate in that community. And you'll see at the bottom, if you have the time to set your display name to your name and organisation, you'll see mine is now David Bott SCI. It just makes people a bit happier when they see who you are. Okay, so this is me when I was young and before lockdown. I don't look so bad anymore, I've shaved the beard off. But more importantly, these are the three speakers. Ian Constance, as I said, Andy Abbott and Mark Bedford. And so what I'd like to do now is hand over to Ian Constance to explain to us why recycling is a really, really important thing. Good morning, Ian. Thank you.
Good morning. Good morning, David. Good morning, everyone. Let me just start by sharing my screen.
Yep.
So thanks, David, for the introduction. As David said, I'm Ian Constance. I'm the Chief Executive at the Advanced Propulsion Centre. We fit in a space neatly between government and the automotive industry, set up by the Automotive Council back in 2013. What we do is we encourage and support innovation into zero emission and low carbon technology into the automotive sector. And we do that by grants for large-scale projects, bringing products into the marketplace, so at the end of that innovation cycle. And we've just started a new initiative at the end of last year, the Automotive Transformation Fund, which also is capital projects, so supporting with government grants, capital projects in building the new battery and EV supply chains, batteries, motors, power electronics, fuel cells, that kind of thing. So exciting times. My job today, as David said, talk about what the economic case for recycling of batteries are and why it's so important to the future of this whole picture. So let's crack on with that. I think there are 5 sort of key points that I'm going to touch on this morning. Limited availability of materials for making batteries, high value recovery from reject cells in the manufacturing process of batteries, end of life vehicle considerations. Is the end of life vehicle an asset or a liability? And then an EU directive, the EU Battery Directive, which will push this whole thing along, as regulations tend to do. and then really wrapping it all up into moving past zero tailpipe for cars into a net zero future. So I think I would expect that a esteemed company such as this would recognize that we are very much on a trajectory now for zero emission vehicles, for battery electric vehicles, and the government's 10-point plan and the cessation of sale of diesels and petrols by 2030 and hybrids by 2035 really accelerates us along that path. Last month, I think we were up to about 18% penetration of sales of light vehicles, plug-ins, and that is just set to rise over the next months and years. So these forecasts, IHS there, relatively lowballing it. The blue bars showing where VW think the European demand for batteries is going to go, and so they say, VW say, by 2030, the European automotive industry will be demanding around 800 gigawatt hours of batteries, up from, you know, a few tens of gigawatts today. So a massive rise over the next 10 years. And the yellow line shows you what capacity that we expect to go in. So falling short of demand, so suggesting potentially a lot of exports unless that gets corrected. And 600 gigawatt hours of capacity going in, and of course we're seeing this all the time now with lots of announcements for gigafactories, and hopefully come quite soon in the UK. I think the key point here is that the cost of batteries is falling very rapidly and has done over the past few years. We're approaching the magic 80 kilowatts per hour, $80 per kilowatt hour, and a continued ramp down from that is going to be important to make batteries at a cost level that's accessible for the mass market. So there are some obstacles on the road, and probably one of the biggest ones that people see coming down the track is the availability of the materials going into these batteries. Now, there are a number of different battery chemistries. I think predominantly we would recognize NMC, so nickel, manganese, cobalt, and with increasing levels of nickel being the predominant form of batteries going into propulsion systems for vehicles right now. And as you can see from this slide from UBS, they are predicting lithium, rare earths for motors, but cobalt, nickel, graphite, natural graphite, and copper to be facing massive, significant shortages within the next 1 to 3 years. Now that, of course, has the potential to stall all of this because, as we know, the laws of supply and demand will say that if the supply of the commodities aren't there, the prices will go up, and that will have a direct impact on the cost of the vehicles and the cost of the batteries. It's not a question of the deposits, it is a question of extraction and processing. Typically, building a gigafactory takes 2 to 3 years. Processing plants take longer, 5 to 7 years, and mines to extract this stuff can take up to This is another slide sort of underlining the point from our friends at Benchmark Mineral Intelligence. You see there the operational supply of some of these key materials in the yellow bar there really doesn't grow that much, and it certainly doesn't track with demand. There's a number of unfinanced projects there, but you see in the mid-20s the recycling ramping up, and that's a factor of the availability of technology, the investment in recycling, and of course the value of these materials going up during that time. But of course, a big gap here on the right, which seems to be unfulfilled. So a lot of work to do in that space. Now, I talked about cell scrap recovery in my 5 initial points, and you might say, well, is this a bit of a sideshow, Ian? And so I wanted to show you some numbers, really. If we're down around the $80 per kilowatt hour, and that stack graph on the left is a Roland Berger assessment of kind of where we are around about now. So 82, nearly $83 per kilowatt hour. And 71% of that is the material cost going into the cell. If you imagine a gigafactory, say with 30 gigawatt hours of production, that's a big gigafactory, but nonetheless, we think that's the sort of scale these things are going to get to. Benchmark rates of scrap out of these, or reject cells, let's say, out of these gigafactories is around 3%. A lot of people running at a lot higher than 3%. 3% are the best, as far as we know. So that means about a gigawatt hour of scrap out, and at 71%, that's material that is a value of around $60 million material. Now, okay, so if you could recover maybe 50% of that, then it's $30 million per annum for that plant. And if you put that in relation to the SG&A on there, 5%, $30 million on 125 million of SG&A. That's a big deal. That's a big deal for anybody. Now, the point about this is that if you're setting up a recycling plant, you want to be close to a gigafactory because you get a base load. You get a base load of known product coming in that you're very clear on how to process, what's inside there. You can talk to the people running the gigafactory, and that gives you a known quantity of business. You might ask, well, why is it that we don't see great rises in recycling from the prior slide earlier, and that's because of the time that it takes for some of the batteries to run through the system. Most cars have a lifetime of say 10 to 15 years, and then there'll be a second life after that as well. So again, if that's going to take 15 to 20, 25 years until you get the recycler coming through, then being next to a gigafactory makes a lot of sense. People to recover the material that's not going to go into productive use in the from the gigafactory. This is quite a busy slide. I don't really have time to unpack it, and I think Andy and Mark will probably touch on some of these points as well. What I really wanted to draw your attention to was that recycling happens at a number of levels, so at battery grade material, at precursor material, but really on the right-hand side of this graph, you see some interesting points here, and that's diagnostics removal and recycling costs are a big part of the overall challenge here. What we expect to see is a lot of different batteries coming from a lot of different vehicles and a lot of different manufacturers, which means working out what's in them, how to get them apart, how to get them to one place is going to be a significant part of the cost and the challenge. My colleagues will be talking more about these. And I'm not really going to get into the processing, but this is just to point out that there are a number of different processes here. Obviously, they have wet and dry processes. They have different levels of cost to them. They also have different levels of being able to extract materials at different levels of efficacy. So end of life considerations are really important as well. Currently, when a vehicle reaches the end of its life, the ELV directive puts the onus on the vehicle manufacturer for the disposal and recycling of that vehicle. Manufacturers have to offer a free take back on used vehicles, and currently regulations require that 95% of the material is recovered and 85% is recycled, and that is the responsibility of the vehicle manufacturers. Now, actually, at the end of a life of an internal combustion engine vehicle, typically the value is around 100 to 200 pounds of scrap material, which means it's not a liability on those OEMs' books. That has the propensity to change if we don't recycle batteries. What has gone from 100 to 200 pound asset potentially goes the other direction and a bigger liability unless we can recycle it. Manufacturers do their bit by marking the parts and ensuring recyclability. That's probably not the case right now with a lot of the EV batteries, that they are easily recyclable, and there's going to have to be a lot of development in that space with the battery manufacturers and with the OEMs to make sure that people can effectively recycle. EU Battery Directive, as I said, the regulations are really important to drive us along this path. The EU Battery Directive has been in place since 2006, but really is going through a big refresh at the moment, recognizing that EV propulsion batteries are going to have a massive impact on the marketplace and aren't really covered effectively in that today. We're expecting that by mid-2024, the directive will require each battery that gets made to be able to clearly describe its carbon footprint, where it's getting its materials from, and how sustainable that really is. And then that will ramp up over time in terms of additional regulations, content and requirements. I just wanted to, I'm running out of time, so I'm going pretty fast, but I just wanted to sort of come back to some of the challenges here. We are, as I said at the beginning, moving very, the focus is on NMC, nickel, manganese, cobalt batteries, I would say. There are alternatives, lithium iron phosphates, manganese batteries, manganese-rich batteries, sodium-ion batteries, and solid state are all in the works. So recyclers are going to have to get their heads around being able to manage this complexity. I think there are challenges. I think that the biggest challenge is going to be managing the different streams as they come on board. NMC is where it's at right now. Fuel cells we see at the higher, heavier end of the market and not really penetrating into the large volume of the vehicle part. And cost considerations, as I said, recycling close to the market for vehicles. So you're not going to be shipping, I don't think you'll be shipping these batteries to Asia or the Middle East or somewhere to do recycling. I think they will occur in the markets where the vehicles are sold. Labour intensive for sorting, I've already mentioned that, and better designs for disassembly. And so finally, my last point was moving past zero tailpipe emissions to net zero, and really here reflect on the VW Dieselgate scandal a few years ago, where public trust in the automotive industry was significantly dented. Everybody thought that the regulations in place were bringing down emissions and bringing down what was their expectations. Now, the thing about batteries and EVs is we have to make it a truly sustainable activity going forward, because I think batteries manufacturing highly energy intensive. The materials have to be dug out of the ground. That's energy intensive. And unless we make these truly sustainable and get to a net zero future, I think the consumer, I think we have the next potential Dieselgate on our hands, and more potential for loss of trust and confidence with the consumer. Another driver for ensuring that the recycling and the true sustainability of this industry gets in place fast. So I think I've used my 15 minutes and a little bit more, so I will stop there. Thank you, and look forward to talking to some of you later.
Excellent, Ian. Thank you very much indeed. If you can stop sharing your screen. Okay, so you've now seen what the scale of the problem is. So now we're going to start the process of trying to unpack what has to be done to do that. And first up is Andy Abbott, who, as I said, is from the University of Leicester, but you can see from his background representing the Faraday Institution as much as anything. Andy, the floor is yours.
Fantastic. Thanks a lot for that introduction, and a big thank you. These are unscripted, these talks, but I don't think I could have scripted a better introduction than Ian's talk. So thanks a lot for that, Ian. That's absolutely perfect. So Reliv is just one of the many projects which are funded by the Faraday Institution. I think there are now 9 of these projects, and we're focusing on recycling, and particularly looking at how to retain value, as Ian's just alluded to. So the Faraday Institution's Reliv project is really split into 3 parts. So First of all, as we've just said, it's partly the metrology, which is, how do you assess what state of health the battery has got and whether it's useful for second life. And then looking at the sort of various methods for recycling. Is it going to be pyro? Is it going to be chemical? We've even got a stream looking at a sort of bioremediation of materials. And then it's actually the wider picture. So a lot of the sort of social sciences side of things, looking at life cycle analysis, the environment, the economics, and also then the sort of the legal drivers to try and change the market. What I'd like to do is to just sort of put you into the position of being a recycler and get to understand the complexity of that process. So the exact date of this analysis is to be determined, as Ian's just said. So if we imagine sort of mid to late 2030s, then when we get to a position where half of the UK's fleet is electric, and we've just heard that currently sales are around about 18%. So when sales are at roughly 50%, then scrappage rates in the UK have been roughly 1 million vehicles for about the last 10 years. So when we achieve a 50% electric fleet, then we're going to be in a position where we're losing about 500,000 vehicles come to end of life every year. And that equates to around about 150 kilotons of material a year, or around about 400 to 500 tons of material a day. So if you imagine that we've got one recycling centre in the UK, and you go to your average out-of-town shopping centre, you're going to find roughly in the region of 1,000 to 1,500 vehicles in that big car park come Christmas time. And you just can imagine that all of those need to be recycled every single day. So how do we build that kind of capacity over the next 10 to 15 years is the question. And also, how do we then deal, as Ian's just said, with that scrap material that's already coming to market at the moment? And that's what we're trying to address as part of Reliv. So if you picture yourself with an electric vehicle in the car park and it needs to be dismantled, then you can take the battery out. And we're all familiar with changing the battery and everything from smoke alarms to computers. When it comes to an electric vehicle, the battery pack is somewhere between about 1/3 and 1/2 ton, depending upon the type of car that you've got. And once you open up that pack, what you'll find is that that pack is split into various modules. And on the right-hand side of that image, you've got 3 electric battery packs. So you've got a Tesla, a BMW, and a Nissan Leaf. And inside of those, you'll have very different structures. So the pack will then be broken down into modules, and the modules will be broken down into cells. At the bottom of the picture, we've got a picture of one of those modules. So this has come out of a Tesla Model S, and this has got 44,000 small cells in it. And the cells that they have vary depending upon the model that you've got, and they also vary with time. But these are called 18650s, and if you ever wonder about the name, it's imaginatively titled because the first 2 numbers are the diameter, and the last 3 numbers are the height in millimeters. So that just tells you the dimensions of it. So we've got roughly 18 mils, so a couple of centimeters by roughly 16. And so you've got an idea of just how small these cells are. And the way in which they pack them into modules is to glue them together with something that looks like polyurethane. So if you've got the picture that you've got to take one of these packs apart, and you've got, in the case of a Tesla, you've got 16 modules, and altogether each module has got 400 cells in it. Think about how difficult it is to actually pull those apart. We're working with Nissan Leaf, and we get a lot of cells from the setup in Newcastle. And when we get down to the module level, even though we're very experienced at doing this, it still takes us 2 hours to dismantle a module into the cells. So a lot of this is due to the way in which the cell is actually put together. So these things are definitely not designed to be recycled. If you imagine that you've got 1,000 of these vehicles waiting in your car park to be recycled every day, clearly they're put together using robots. And so the logic says that we are going to be in a position whereby we're going to need to pull these things apart using robots. As part of the Reliv project, we've got this robotic system. It's autonomous and is able to identify the type of battery and where all the fixings are. So we're now completing that test facility in Tyseley in Birmingham. And what we're also able to do is we've now got a neural network which can assess the different states of each of the different modules within the overall pack, so that we can look at which cells or which modules need to be replaced, or whether the whole cell is, the whole pack is dead. So we've been developing different techniques for looking at end-of-life applications and also recycling protocols. Also in University of Birmingham, we've now got the only UCAR 7 rated battery test chamber facility in the UK. I think it's only one of two in Europe, where we can not only pull these packs and modules apart, but we can also shred them. And this is all within a very safety contained facility at the University of Birmingham. So let's say we've now pulled our pack and our cells apart. Where does the value lie? What are we looking for to be able to get value from our material? And what we can see is that, unlike a lead acid battery, we've got 10 components instead of 3. So lead acid recycling is dead easy. We've got polypropylene, sulfuric acid and lead. And all we need to do is to open the structure up. We've got grids of lead, we've got a casing of polypropylene, we smash the thing up, and lo and behold, polypropylene floats, lead sinks. And so separating those two into pure streams is dead easy. And so we can get 99.9% of the lead recycled. The difference in properties in terms of density between lead and polypropylene is huge. If we try to do that with a lithium-ion battery, a lot of these materials are very similar in terms of their density, in terms of their electrical properties, in terms of their magnetic properties. And so separating those materials into different value streams is in fact very difficult. But as everyone knows, what we're after is that cathode material where the majority of the value lies. And coming back to Ian's presentations, what we've done is a retro economic analysis, which is to look at how much can that recycling project cost. And a very surprising number is that the total cost of dismantling, the labor cost, the equipment, etc., has got to be in the region of $2 to $6 per kilogram of battery material. And although that sounds quite wide, it's quite obvious why that is. Depends upon the cobalt levels and whether you're looking at something like lithium iron phosphate as a material which has got a much lower value associated with it. So I want you to keep in your head that sort of $2 to $6 per kilogram, because that's a very important number in terms of break-even points on the recycling. So Ian's very nicely introduced this concept of having either pyrometallurgy, hydrometallurgy, or mechanochemical separation. And there are advantages and disadvantages to all of these. And although you might sort of think, well, actually, this is a long way away, and the difficulty, as we've already heard today, is the amount of material entering the market, we can actually take a lot of solace from what's going on in China. And I've got a fantastic Chinese postdoc who reads absolutely everything in Chinese, including the patent literature. And so we know that in China, they've just opened in Hunan in April. And obviously, there were other things going on in Hunan in April last year. They've just opened a $178 million plant capable of processing 100,000 tons a year. So just to give you some idea, so it's taken them just over a year to be able to open that plant. But that is one plant which will be able to cope with pretty much where we expect to be in the UK in sort of 15 years' time. So for us to be able to develop this facility is possible. To be able to do that economically requires then the next sort of step forward. And I think the Chinese are sort of light years ahead of where we need to be in Europe. So what we have gleaned from the Chinese and South Korean literature is that there's a lot now being done on rather than shredding, which tends to be what's done in Europe and America as that first stage, which is what is routinely the process for the lead acid battery. What they tend to be looking at now is a lot more in terms of separation. So getting the individual cells, opening the cells, separating the anode chemistry from the cathode chemistry, and then what you end up with is a much purer stream of material. Therefore, you've got greater value within your stream. Clearly, this is difficult with the cells we've got, and the reason for that is mostly due to these binders and due to the cell structure. But you can see quite clearly from the way in which the Chinese and South Korean literature is going that they're designing cells which are able to be dismantled rather than shredded. So recently we've just completed a techno-economic analysis looking at processes published in the literature, and we took 5 processes which used shredded material, and we analysed the economics of that process. And what we found is that you could make a cost saving of somewhere between nothing and up to sort of 20% by dealing with that shredded black mass. Whereas if you actually took a disassembled cell, because you've got a much greater value, much higher purity of material, then your cost saving with respect to virgin material was between about 20 and up to 85%. There are some caveats in that, but what we can see quite clearly is there's a significant economic difference between shredding and disassembly, and this is why we think in the Far East there is this move towards disassembly rather than shredding. So what I'd like to do is you're actually quite fortunate, this is the first time we've decided to show this, is we've come up with a novel method whereby we can take a separated electrode and turn it into its constituent components really rapidly. So to give you an idea of the speed difference, if we were to take a sort of shredded material and put it through a standard hydrometallurgical process, we can process around about 100 times greater material in a given volume, given time, than would currently be done. And what we're doing here is a process which is very similar to your trip to the dentist. We're using ultrasonic processing to break the adhesive bond between the active material on the electrode and the current carrier at the bottom. So this is a brand new technique. And what I'd like to do is to show you, hopefully this video will play here. So here's the electrode going in one side, so this isn't speeded up. And you can see in around about 5 seconds, we can get the electrode to come out. It goes in black. And when we pull it out, in this case, it's the anode material. We did that just because it looks visually better. And we can see that in 5 seconds, we can in fact delaminate all of that electrode material. So we can recover 99.9% of the electrode material from that using nothing more toxic or expensive than water and ultrasound. And in case you think ultrasound sounds very difficult, it's a standard technique. So every single sandwich that you buy in the shops is in fact cut using ultrasound. It's a very common, simple and cheap technique. So we've been able to take this black mass that comes from the electrode surface, we've been able to repress it into new electrode material, and we're currently testing these materials from scrap material to evaluate the properties of these cells. So you can see it's a very simple, cheap and effective way of recycling these electrodes. And like I say, you're the first people to actually see this piece of technology today. Just to give you some idea of, like I say, what's happening in the Far East. So you saw the very complicated structure in a Tesla cell. This is a pack from a new design from a company called BYD in China. And they've got what's called a Modulus cell. So we've got around about 40 of these, what they're calling blade cells. So rather than having these sort of 18650 small cells, to give you an idea, those blue cells that you can see in the middle picture on the right are around about 1 meter long. So they look like a blade. And what they have is, rather than having lots of different glues to stick the pack together, these things clip in, and so they're simple to clip out. And we're calling this a sort of Christmas cracker arrangement, where you've got anode chemistry at one end cathode chemistry at the other end, and you can pull the two chemistries apart and very simply separate those chemistries. So it's very clear that what we need is a cell that is designed for recycle. And there's an article here at the bottom, published about 6 months ago in Green Chemistry. It's the first article of its kind. It's in open access, so everyone can access it. And we go through all the different aspects of cell design, what's wrong, how all the OEMs are making different sort of connectors. And this is really the complexity that we've got. But we can see, I would have thought that in 10 years' time, what I'm showing you here will become commonplace, and this Modulus pack will be the way forward that all manufacturers are talking about. So as I say, part of the Reliv project, we're not only looking at how to physically and mechanically separate the cell, we're also looking at a lot of the social aspects in terms of the legal side of things, transport safety, protocols for second use, the logistics, so where will the factories go, and we've modelled different scenarios, whether we've got 1, 2, 5 or 10 recycling centres in the UK. Just to give you an idea, compared to the lead acid business at the moment, there are around about 10 recycling sites in the UK. By the time we get to sort of 2040, the lithium-ion battery recycling market will be at least 10 times the size of the current lead acid battery recycling system. So you get an idea of why logistics is such an important thing. Question of ownership models is really important. And then we've looked also and published a lot about Brexit and its effects on recycling. So because I've also come to the end of my allotted time, hopefully what I've shown you today is how battery design really is the crux of creating an efficient recycling market. The big problem that we've got to try to avoid in future is glues. We've got a project at the moment looking at recyclable glues that we can debond. Solver mechanical is the method we think is the best way forward, and looking at selective binders which are simply removed. We've got systems which will now delaminate both anode and cathode material using just water. So although cell longevity is important, we've got to get the customer used to a reliable cell. What we also need to make sure of is that this works economically and it can be recycled on a very large scale. Thanks for your attention.
Absolutely brilliant, Andy. Thank you very much indeed. And you're right, it's amazing how much you and Ian complemented one another in the things you said. So last stretch now, hear about from Johnson Matthey, a company that's been recycling metals in particular for many, many years and is very much a big player in the system. Mark, time to share your screen. Okay.
Good morning, everybody. My name's Mark Bedford. I'm the director for battery materials recycling as a business development project within Johnson Matthey. Johnson Matthey overall, as I think everybody's aware, or we try to make everybody aware, we have this vision of a world that's a cleaner and healthier place tomorrow and for future generations. The way that battery materials recycling really fits into this is part of our history and the legacy of what we do. So we are the largest refiner of secondary platinum group metals in the world. So we operate within complex supply chains, and we process and manage materials on behalf of our customers. We know battery science. So we know battery science, we understand what happens in that, and we also have a background in the automotive industry. So what we're trying to do is use our knowledge, our experience in recycling, and the knowledge that we take from PGM recycling in developing solutions for battery materials recycling. So what I'm going to look at this morning is we are facing really, I think, 3 key challenges in this area. The first one is really around safety. The second one in terms of the supply chain, and the third goes under a sort of a generalized banner of technical. And on the right hand side, you can see there, we're using these things, our science and technical expertise, manufacturing excellence and global supply chain, the history of metal procurement and management, and this 40 years plus experience in the automotive supply chain to go after these challenges. And what I was thinking about when sort of putting this talk together was not to try and make it sound too negative, in the sense that everything that we face is a challenge and a problem, but there are some very specific challenges around this, which I think Ian and Andy alluded to in their talks as well. So I'll go on to explain what those mean in a little more detail for us. So if we go on to the first one, just to explain this value chain as we see it, you'll see very typical diagrams like this in all discussions of battery recycling. We start in the sort of top right-hand corner with the OEMs and battery owners having a sort of economic drive around this from their extended producer responsibility. In the bottom right-hand corner, there's a huge and important sector around the battery services, around the handling, dismantling, and inventory management of end-of-life vehicles and end-of-life batteries. And a lot of cost is going to be incurred in that area. As Johnson Matthey, we operate mostly in the bottom left-hand corner. This is fine refining of black mass, which Andy referred to earlier, which we still believe is going to be produced in substantial quantities, regardless of the sort of direct recycling technologies that are developing. A lot of the batteries being made today will end up as black mass at some point towards the end of this decade, we believe. And those processes have to be low CO2, produce materials at high purity, and they need to be able to compete with primary flows of materials as well. For us, the critical part of this, and in this target that we all have of having a closed loop recycling, is to make the link between that fine refining process and new battery manufacturing, and being able to control the purity and capability of the material that emerges from the recycling process to be able to recycle it back into cathode and cell manufacturing to close that loop. And it's that critical link that we're most carefully trying to position ourselves as being. One of the things we wanted to focus on really is the safety aspects of battery materials recycling. I mean, safety is a #1 priority, is the #1 priority for our company. And there are some really significant safety issues around battery recycling that we shouldn't overlook. As we've mentioned already today, and Andy's measured, these batteries have not really been designed with recycling in mind. The safety challenges can broadly be categorized into electrical and chemical. The safe handling of end-of-life batteries is going to require significant attention to electrical safety, some very specialized equipment and training. We've seen already some fairly hair-raising things going on in the industry, and I'll come to a point at the end about what the significance of that is, but there's a lot of work to do around electrical safety. Our area is perhaps more in the areas of chemical safety, and these batteries are a veritable panoply of hazardous and difficult materials. So we have organic compounds such as the PVDF binders, and sensitizing metals such as nickel and cobalt. Things like occupational exposure are going to become very, very important to this industry. We come from a place where platinum is one of the a major health and safety challenge, in the fact that it's a respiratory sensitizer. At the moment, we are designing new refining processes to handle platinum at very, very, very low levels of occupational exposure to those materials. And we can feel the same thing coming down the path for both nickel and cobalt, as they are too respiratory sensitizers, amongst other things as well. Perhaps more immediately adjacent is the challenge of fluorinated compounds such as LiPF6 in the electrolyte. This readily hydrolyzes in the presence of water to hydrogen fluoride, and hydrogen fluoride is possibly one of the most toxic and corrosive and challenging materials you could ever see in any sort of refining process. There is no really safe level for exposure to hydrogen fluoride. It's both toxic and corrosive in almost equal degree. And inevitably, when you're dealing with some of the fluorinated materials in batteries, you are going to have to deal with hydrogen fluoride at some point. So there are the immediate issues around protecting life and limb, making the battery process safe as we possibly can, but the industry also faces a reputational risk that we're going to have to deal with. It's going to be no good if there are repeated fires, there are repeated cases of thermal runaways, of batteries not being handled correctly. The whole industry is going to face a reputational risk that we are going to have to tackle very early on and head on. If you just go on to the next one, please. As far as the supply chain is concerned, it's really yet to be established, fully established, and it's going to involve a lot of new participants in the industry. In the PGM recycling industry, it's more than a century old now. It's based on existing relationships of trust between the participants. Those have yet to be established in battery materials recycling and need to be in the future. Another thing that we're very much used to doing in PGM recycling is everything is aggregated, everything is blended, everything is put in a big heap so you can deal with it in one go. The point thing you have to do in terms of battery recycling is there needs to be full traceability of the material through the supply chain. And everything that we normally do in terms of aggregation tends to be something that will reduce traceability of the material through the supply chain. So that's something we're going to have to deal with. Things like representative sampling and accurate analysis are going to be no less important in battery materials recycling as they are in the PGM industry, even though the intrinsic material values are going to be lower. You need to know what you're dealing with, and you need to be able to sample in a representative way the material to be refined. I think this point was touched on earlier on at the moment. The actual commercial return available for each member in this supply chain is not really clear at this point. And one of the problems that we're all wrestling with is that uncertainty can delay important investment decisions. If you don't know if you can make money out of this at all, it's very difficult to unlock the investment that we need to make sure that this industry exists in 10 to 15 years' time. Our view was and is that the operation decision risk about the entry into battery materials recycling is going to require partnership and consortia as a likely way forward. We don't feel that any one company is going to offer a solution from end to end. And in terms of the risks involved in investment, partnerships and consortia are definitely going to be the way forward. Yes, so the technical risk very much around the purity of the material that has to be produced. And I think Andy made a very important point earlier on. One of the challenges around shredding, which is one of the popular processes to produce black mass and the material that is going to need to be refined, is that it tends to be a process which introduces impurities into the cathode materials as they are recycled. And as we introduce new materials to do the separations and the purifications needed, the effect of the unknown impurity and the material which has to be recycled is going to have it is a major challenge in terms of the processes that we actually need to use. One other thing to mention is that a lot of the refining processes that have been tried to be developed so far have been really developed around what I would call surrogate feeds. They're feeds which are not particularly typical of the kind of materials we're going to get from the basic recycling of materials. So there are a lot of claims being made at the moment for new processes in recycling which will not survive scale up. And that we see as a major issue as well. And of course, in a lot of the processes that are being envisaged, there are substantial challenges about the production of wastewater and other effluents from hydrometallurgical processes, which means that it's not only carbon and the carbon life cycle that is important in these processes, but it's also the handling of wastewater and other effluents that are going to emerge from these processes, which will come out of scale. So just moving on to my conclusion, the large-scale recycling of end-of-life batteries is both a challenge and opportunity on an unprecedented scale. There is enormous opportunity for what they call urban mining. The point about a battery is you are bringing a very large quantity of the materials that you need back to the place at which they're needed, which is, as we mentioned earlier on, adjacent to the cathode manufacturing plants and hopefully the vehicle assembly plants. And that urban mining has a potential to have a significant impact on sustainable resourcing of the electric power chain. Our experience in PGM recycling informs this challenge. It doesn't actually provide a huge number of solutions around the challenges in all areas by any means. I mentioned before that this need for collaboration and successful partnerships through the supply chain is clear. And although this kind of tidal wave of end-of-life batteries that we've talked about is maybe a decade or even more away, there needs to be some urgency around the formation of the ecosystems that is going to deal with it. One of the interesting points I think that came out of Andy's discussion was this idea that batteries are going to be designed for recycling, that compositions are going to change, and so on. The fact is that a huge pool of materials using existing NMC technologies, LFP technologies are being made now, which are going to need recycling in 10 or 15 years' time. So there's a major opportunity to deal with the batteries that are being made now and will be made in the next 5 years in that 10 to 15 year time frame. And my suggestion is we need to act now to get that capability to deal with those materials in place within the next few years. We don't have another 10 to 15 years to think about it. So sorry for the clunkiness of the presentation, but that's the end of my little presentation in this workshop. So thank you for listening.
No, Mark, that was excellent. I apologise for the problems, but I sometimes think Microsoft do it on purpose. So I mean, what you've heard there is a really good balance of people in the field. You've got the economic drivers, the need to do it. You've got an overview of the technologies, and you've got some very wise words of the problems you need to address. And Mark is right. These are problems you need to address if you're going to be successful. So we've all got now a much better view, hopefully, of the opportunities, the needs for, and the challenges we need to address in the recycling system for batteries. Not least of which, as all three speakers have pointed out, the underlying technology may well change at some point in the future, but that then gives you a legacy problem. Great thanks to everybody. The recording of the main event will be up on the website within a week. We're going to use the recordings of these individual things to make sure we have covered every point. And you know, one of the things we're planning, you probably realise that Robin, Andy and I operate as a sort of triumvirate of these things. The next workshop will probably be on next generation technologies, because there was all the questions about, you know, what are the advantages and disadvantages, when will we move, why aren't we moving sooner? And Andy just mentioned the fact that it's beginning to be a bit of differentiation in the market and things like that. So, you know, watch that. Do please, if you know other chemists who might be interested in what we're doing in these series of workshops, let them know. The idea here is to build a community of people in chemistry who want to help address this big opportunity you've now all had unpacked for you. And yeah, we will continue to run these workshops with people. We also had a request, rather interesting request, about the difference between the European and UK thing, and a strong recommendation for a good speaker on that. So yeah, there will be a series of workshops over the next couple of years until, you know, the problem is either solved or we have no automotive or battery industry in the UK, because we don't give up very easily. But I mean, thanks again for coming. If you have any questions or issues, please contact us at the SCI and we will try and address them. But thank you for your time. We're getting to the end of you know, 2 hours, so it's time to let you go back and have a cup of coffee and unzoom for a few minutes, probably before your next meeting at 12 o'clock. Thank you very much for your attention. It's real special thanks to Ian, Andy and Mark for truly excellent talks.